So I think we're going to go ahead and get started today. Thank you so much for joining us. We are happy to have you on our webinar overview of the TigerGraph database and analytics platform. We have a few housekeeping items to go over before we start today. And obviously all of you are muted right now. So if you have any questions, go ahead and use the chat feature, or you can use a Q&A feature to ask us questions, and we'll answer those questions after the presentation. The webinar is being recorded, and we will send you those slides and the recording link in email probably tomorrow. And let's see, so I'm going to introduce to you our speaker today. And it's Victor Lee, and he's our Director of Product Management. And as you can see, he has a very strong academic background, in addition to decades of experience in the technology sector. So Victor, thank you for speaking with us today.
Thank you for the introduction, Emily. It's great to be speaking with you today. As she said, I've both grew up in the Bay Area, attended school there, worked in Silicon Valley for a number of years, and then went off to grad school and studied graphs. So I've been deeply absorbed in databases and graph data for about the past 10 years. And I was really excited to join TigerGraph about 3 years ago. And today I'd like to share with you what TigerGraph is and is all about. So this is our agenda. We're going to try to do quite a bit in the next hour. Talk about Deeplink Analytics and why that's important, and why TigerGraph is able to deliver Deeplink Analytics with its native parallel graph design. Cover a couple use cases, and then demonstrate the system for you live, and then address some of your questions. So, we live in the big data age, as everyone knows. We are surrounded by data, and that is because we've digitized so much. Not only do we produce our documents in digital form, but we do our transactions and talk with each other, both on audio, video, chat. Everything is some form of digital information, which can be recorded. And because storage is now cheap, a lot of it is being recorded. And so not only do we have data, but we have connected data. Everything can be thought of as a network. So a lot of you know this, and for those of you that are maybe a little bit outside the big data industry, big data is not just about having a lot of data. It's about using that data to gain insights and to deliver more customized, personalized results. And the attributes that you have are not just volume, but variety. So that gives you a very good statistical distribution of what the full world is. So you can produce more accurate models, do better machine learning. Data is also coming in very rapidly, as we said. So there's a constant flood of new data. So we can store it, but can you analyze all of it? Can you do real-time processing? So that's another challenge. And again, we are in the networked age. Someone said decades ago, the medium is the message. And so that's key. So the content of your message isn't everything, but it's also how did it get to you, from where, when, in what way. All those connectional attributes are important. So a graph database helps you to connect the dots. So a realization that a lot of people are coming to is that a graph database is really a better way to handle your data analytics needs. Not for everything. We're not gonna remove relational databases. We're not gonna replace them, but it's taking on a lot of tasks that were being done before, or it's opening up new opportunities. It's able to handle things that weren't possible before. So you have this connectional database. You have this information that's inherently a network. A graph, the term graph comes from graph theory in mathematics. Graph is just the mathematician's word for abstract network. So your data is a graph. It's also how you want to analyze and perform computations, because the computations actually want to traverse the graph, as we say, to move from one entity, one node, and see how is this related. I'm a customer. Which products have I bought? What other customers have bought these products, and what other products have they bought? That is, in essence, is a product recommendation. That is a graph operation by going both back and forth between products, maybe the way those products have been tagged, when did you order them, where were they delivered, etc. However, so the idea of graph databases has been around for a couple years, but they didn't do everything that people wanted. So TigerGraph looked at what was missing in the market, and we came up with these 3 key features that customers needed. They needed real-time processing, they needed Deeplink Analytics, and they needed scalability. So real-time processing. Can you do customer engagement while the customer is online? Can you catch fraud while it's in progress? Can you ingest that very rapidly arriving data? Because your transaction itself is new data. Can you bring that in real time so that the subsequent activities will take advantage of that new data you just received? So a lot of applications need some sort of real-time processing, and real-time is relative. It might be sub-second. If you're doing a large analytical query which used to take hours or days, if you can cut it down to seconds or minutes, that's another form of real-time processing. We also need deep link analytics. If you want to get a very deep understanding of your world, you want to take advantage of that big data, you have to explore a lot of it. And so we think in a graph, we talk about hops. Every time you follow a connection from one node to its neighbor, that's one hop. And then if you make another connection, that's a second hop. Being able to follow as many hops as you want in one query is really what you want. We found systems from existing designs that really petered out after only 2 hops. So we said, and talking with our customers, they said, we need to be able to do 3, 5, 10 hops in one query. And thirdly, scalability. Data is growing. You may be able to fit all your data on one server today, but tomorrow you're going to need more servers just to store the graph. So we need to be able to provide a system that easily scales out as well as scaling up. So summarizing the 3 needs, customers need a scalable, real-time, deep analytics system, where deep analytics means the ability to handle a query with 3 or more hops. This comes up in a wide range of applications, including but not limited to AI and machine learning, which itself is being used for many things, such as fraud and risk management, recommendation, supply chain logistics, etc. TigerGraph is pleased to be able to deliver on all 3 of these using an architecture that we call the native parallel graph. The native parallel graph is our custom design for graph storage and parallel processing. So we designed our own storage engine. It's custom designed, particularly so it is a native graph. It's not some other design which with a middle top layer or surface layer to make it look like a graph. It is at the lowest level vertices and edges. It's also designed from the ground up for parallel operation. You have a lot of data. A typical query, you start at maybe 1, maybe many vertices, but then you go to their neighbors. And each time you go to the neighbors, you're probably increasing the number of vertices because you have several neighbors. So you're crossing hundreds, thousands, millions of edges. It's growing exponentially with each hop you take. So you need to be able to process all that very efficiently. Thirdly, what we also did was we compressed the data as a built-in feature. When data is imported into TigerGraph, it's usually 2 to 3 to 5 times smaller than the external data was, than your raw data. Compared to some other systems, that might be 10 times smaller. The advantages are twofold. One, it reduces your hardware needs. But second, and very importantly, it allows you to store more of the graph in your memory and in your cache. And that's going to reduce your data access times. That's going to give you higher performance. So compression, both hardware and computational performance. So again, our native parallel graph, we came up with a unique system where every vertex actually becomes a little computational unit. So when you're processing a query, the computation is inherently distributed across multiple threads as it's traversing the edges and then performing computations to do a complex analysis on each of the vertices. So the native parallel graph is efficient and scalable. But another key element to achieve the Deeplink Analytics is our GSQL language, because you have to be able to harness that capability. So what is unique about GSQL? It's expressive. It's designed not just for traversing the graph, which it does very well, but also for performing computations. It has built-in parallelism. An old adage in a couple decades ago, trying to program parallel algorithms was considered a complex art because you really had to understand at a low level what was happening. It's now, GSQL makes it very easy. And lastly, though you won't see this, but just know that under the hood, our language and our database platform in general is implemented in C++ for efficient memory management and for just the best possible performance. And if you are interested in adding user-defined functions, you can supplement the features in the language with your own C++ functions. So lastly, as I already mentioned, we have this native parallel graph. And I'm going to try to keep moving because I want to get to a demo of showing you the system as well as talking about some use cases. I'll just quickly talk about the overall system design. On the top side is the user interface. We have GraphSQL, the GSQL language. We have Graph Studio, which is our visual user interface, which can be used both for graph design, graph analytics, and graph visualization. And for embedded applications, we have REST APIs. We can import data from any number of different sources as long as you can present it in some sort of text format. We can, particularly tabular format makes it very easy. And then our output is delivered in JSON, which can then hook up to whatever other applications you have. The system can run either on premises, on Linux servers, or on cloud servers, or on some hybrid. And this isn't just a database, but it's really a enterprise-ready platform. So it integrates easily with other applications, as I said, with the REST APIs. We have sophisticated access control, both role-based and database permissions. We support data encryption. We, of course, have ACID transactions. We have system monitoring and alert features. We support HA and fault tolerance. We can hook up with other data storage services. And I mentioned we are scalable, so of course we can run as a distributed graph across multiple server nodes. These are just a few of our customers that are in production. The company was founded getting close to 6 years ago. We just launched publicly several months ago, but so during that time of our existence, we have signed up several companies across a wide range of applications. So I'm going to spend about 5 minutes on use cases, 5 or 10 minutes, and then I'm going to get to the demo. So case one is building an enterprise knowledge graph. Like many companies, so I think this one a lot of people can identify with. You have numerous data silos, different divisions of the company or different departments have their own data sets, their own databases. They may have in different formats running on different platforms, and so it's difficult for them to share. The company realizes if they could merge the information into one data set, not only would it provide easier access, but it would enable analytic capability that they can't do right now. Right now, they can't analyze across the data. So what they wanted to be able to do, and what TigerGraph was able to provide, is to merge all the data sets into one graph database. And why, in particular, TigerGraph made this possible is for 3 reasons. Our platform provided fast and easy import, about 1 million lines per second. And the data modeling was flexible enough that it was easy to take these different data sets and merge them into one common data set. Secondly, they had a relatively big graph, but it required only a small hardware footprint. So 3 billion vertices, 6 billion edges was handled with just one server with 64 CPU cores and 64 gigabytes of memory. And with that system, they're then able to provide and implement sub-second queries. These are just examples that used for benchmarking. But the real need and the real power is now they can see how the different how operations run across the business. They can learn from across the business. So it's providing enterprise level knowledge, enterprise level analytics. This is really sort of the core case for what can you do with big data. Case 2 is real-time fraud detection. So China Mobile is, I'm pretty sure it's the largest telecom company in China. And as you know, that makes it the biggest telecom company in the world. One of their problems is phone scams, as it is with any telecom in the world. So, people are trying to sell you something or the activity is fraudulent. The key is that they hit hundreds, if not thousands of people. It has a big effect on the customer base. So they came to us to see if we could provide some sort of solution to help them detect and take action on fraud. So what we were able to help them implement is a real-time machine learning and decision system. This has a couple elements. First, they had to construct a graph of all their phone calls. So every single phone call is logged into this database. So it requires real-time updates. They keep a sliding window of the past 1 or 2 months of phone calls. That constructs a database with like 10 billion edges. So one edge per call. 300 million new calls per day. And along with that, so they're adding the edges to the graph as they come in. They're extracting features from the individual calls and from the set of calls and adding those to the graph. To handle all this data, they used a 5-server implementation, and each of the servers handles about 2,000 calls per second. They then do real-time machine learning, and real-time in this case means they take a sample of the data every 2 hours and use that to train the data to build an up-to-date model. So what are they looking for? The particulars are somewhat proprietary, but in general, what does a phone scam look like? It's a rapid number of calls to a wide distribution of recipients for whom the caller may have no prior social connection. That's a typical profile, as opposed to normal social calls. You're calling people you know, so there's a repeat business. Whereas in a scam, that it's not. It seems like unique burst of events. Second, you need to deploy real-time decision making. So whenever a call comes in, using the model, they apply the model to a call, and they're able to alert the recipient if the caller fits the pattern of a phone scammer. And so this system has been in production for over a year now. And lastly, case 3 is a transaction and social graph for analytics. So we worked with a company that it provides local delivery services, but it's a global business. So they have hundreds of thousands of delivers. So you could call them drivers because they're using vehicles to make the deliveries. Hundreds of millions of customers, and over time they've had 5 billion or more transactions. So they had a couple problems they wanted to solve. One was they have fraud or abuse rings among the customers and employees, and they want to be able to detect that. Secondly, just a general desire to analyze the service patterns to help them improve their operations and their compensation models. And thirdly, as we said, the data set is large. It's also very dynamic. It's changing all the time. There's a lot of turnover. Transactions are being conducted at a very rapid pace. So they needed a database that could be very quickly updated, and they also need something that could do Deeplink Analytics to help them detect the fraud. So we able to construct for them a system with 20 machine cluster that loaded 2.2 terabytes of data in 3.5 hours. And it can perform deep link queries, in this case 4-hop queries, which each one, because of the exponential growth in the number of edges, traverses 100,000 edges in a fraction of a second. So overall, about 10 million edges per second in a graph with, I believe that, I think it says 22 billion edges. I need it. That might be 2.2 billion. I'll have to double check, sorry. Just an example of the queries when I said 4D. So start with one user who has, in this case, a driver who has executed a trip, and the trip is associated with a phone call, the person, how the trip was ordered, how it was paid for, and then we see connections to other users and other drivers. So they wanted to see, following all possible connections like this, to find the users at the end. And then it's not shown here, but as a second step, it would analyze to see if are there connections among these users which are 4 hops away from the input person. And just some benchmark data showing how many of such queries we were able to handle per second. So it's in the range of 2,000 to 5,000 queries per second. So I've spent about 30 minutes on the slides. I think it's time to kind of get to our live demo. So what I'm going to show you is actually available for any of you to take a look at on your own later on. It's at testdrive.tigergraph.com, or you can just go to our main website and click on Try It Now. So this is our test drive system. We have 5 different use cases set up here. Each one is an instance of the TigerGraph system running live on Amazon EC2. So each data set is running on a single server. Some of the data sets have billions of edges and vertices. So I'm going to show 2 of them to you today. The first one I'm going to show is the social graph. And just because this one has the most interesting schema. I'm going to walk through quickly the 5 different steps that Graph Studio has broken down the design and analysis process into. So again, Graph Studio is our visual user interface running on a web browser. So to use the TigerGraph system, you have your choice of using Graph Studio, or you can, of course, do work on a console, typing your commands. And once you've done that, you can deploy them using REST APIs to work in an embedded system. So the first step when you're designing a database is design your schema. So this is a social graph schema. It has a citizen or person in the center, and then connections to multiple other types of nodes or vertices. Home address, phone number. But this particular data set is also designed to track activity to see if there is some relationships, possibly improper relationships. So there's a report case referring to police filings. There are what transportation did they use and where did they stay. So I think there are about 10 different connections with this central person. To create a new one, you would just click on the Add Vertex Type, make it employer, add an attribute, so creating new vertex types or edge types is that easy. Once you have your schema, the next step would be to load data in. So in this case, what we've done is we've named a bunch of data sources. Each one shows up as a little file icon. And then you make connections between the file and the vertices and edges in your schema. And after you make the connection, then you just click on one of those connections and it pops up these tables. And here you just map out the relationships. So on the left, this is an input data table, bank transfer records. It's in CSV format. So it has 5 columns. And then this is the target vertex or edge. I don't remember which one. I think it's vertex. So it has an ID and 2 additional attributes. And you literally just draw these connections. It's also possible to add functions. There's a function library over here. So this is a concatenation function, which is taking these 3 different time and string and numeric attributes and combining them as a string into make the bank transfer ID. There's even more sophisticated functions you can perform if you use the full GSQL language in text console mode. Then you can load your data, and I just wanted to show you this data has already been loaded, so it has 1.2 billion vertices and 4.4 billion edges. You then have two ways in Graph Studio that you can work with your graph. You can do free-form ad hoc exploration, such as if you know a vertex ID, you can, actually, I might not getting a good vertex name. So let me do some I was going to say the other mode is to have it randomly select some vertices for you. Okay, I guess my vertex names were too long. So here are 5 vertices. You can then, as it expand upon them, to see who are their neighbors. I will do 2 levels of expansion. And it's a lot. So let me see if I can clean it up. So you can see each of the clusters. Those are the persons. You can see each has a little network of other relationships. And in some cases, you see that the clusters have been connected. We can also do a shortest path connection. Let me clean this up. Let me start again to make that a little cleaner. Let me pick a couple random persons here, and let's just see if there is any connection between them. So start there and start there, and show any paths up to length 6. Didn't find one. Let's try 7. And lastly, let's try 8. Oh, I struck out. Let's try this person. Not doing so well. That's what happens when I just pick random things. So, but, I wanted to show the query. There's another, so you can author your own queries. So here is an example of our query language. It's called GSQL again, because we have structures like SQL, select from where. The accum clause is where we do our parallel computation. And the language is enhanced with procedural structures like where, conditional statements like if, then, else. And the whole thing is saved as a parameterized stored procedure. So you can then run the query. So let's run the query. And here is where I will throw in a couple random numbers. Okay, so what this found was it found connections between these two persons. And some of these connections are very long, as you can see. I think there's a path going from here to here, following. These tend to be in multiples of 4 because of the particular graph design. So this one's probably 16. To make a connection from one person to another person via a phone call takes 4 connections. If I zoom in a bit, between here and here, money transfer. So this person's bank account, a money transfer to another bank account to another person. So it's 4 links to get from there to there, just to neighboring persons. So again, it searched a database of about 4 billion edges and 1 billion vertices, and in a fraction of a second found these very long paths of like 12 and 16 links. I'm going to jump to another demo because it has some additional queries. So the anti-fraud case, the schema here is we have a user, we have transactions, we have what did they pay with, like a credit card, and what physical device did they initiate the transaction with? These are electronic transactions, so in a lot of cases, the device is a smartphone. Might be their home computer. Oh, again, so this data set also has roughly the same size, about 1 billion vertices and 4 billion edges. Circle detection is a fun one. In this case, we're looking for fraudulent activity where money may be being transferred from person to person through a long series of transactions, and then some of the money comes back to the original person, making a loop. If it's just a small fraction, that may be normal activity, but if it is a significant fraction of the money that's coming back, then it looks like money laundering. So you can see that we found dozens of loops. Remember, the red is a person, green is a transaction. So it's so many that it's actually hard to visualize. So we can try to change the layout. That gives you a different view. And also, you can also see the view as text just by switching to the JSON output. So here you can see the amount of each transaction, when it occurred. This is a timestamp, and going from which account to which account. So for more automated processing, you could take advantage of the JSON output. And if you want to get a visual impression or do some more visual exploration, you can use the visual interface. I think I'm going to show maybe 1 or 2 more queries and then open it up to questions. So if I go back to the queries, this one is designed so you enter in one transaction ID. So a transaction has both a sender and a receiver, and then we explore the clusters around each of the two, the sender and the receiver, and we look to see if there are any additional connections between those two clusters. So in this case, we didn't find anything between the two clusters. Let's try this one. Again, nothing there, but nothing there. Okay, in this case, it found one additional connection between the two clusters. So this is the input transaction, and then sort of on the left is sort of the sender's network, on the right is the receiver's network, and from that network to that other network, it found one additional connection. And so if you found many such connections, again, it would require more advanced analytics to be sure, but sometimes that may be a clue towards some sort of fraudulent activity, possibly money laundering. It's really sort of application dependent, but this is another example. So I'm going to hop back to the slides. And
great. We do have a couple questions, Victor.
Okay, great.
So they came in via chat and via the Q&A. So let me just, I have the ones from the chat. So one of them is, can TigerGraph run fast analytics queries for the entire graph, or does it need to identify a subgraph to do fast processing?
We are designed to do run full, however you want. So we've done benchmarks with both full graph analysis, so traversing every single edge in order to, say do feature extraction to build a model. We can also do single point source queries and do those efficiently. And because we have again, when I say we're designed to run multiple transactions as efficiently as possible. So those of you that have some database experience, our locking model is very fine-grained. So we can actually be processing multiple transactions at the same time, because as long as they're not touching the same data. Or we can do a full graph analysis efficiently. And we're not limited in that way, that like some NoSQL platforms are really targeted at a certain type of analytics. The original MapReduce is designed for a particular type of analytics, and it was not a great general purpose system. But we try to make something that is very general purpose.
Great. So another one is there a plan to support Gremlin or maybe Cypher as query languages?
That's a good question. We get that question a lot. Our initial reason for implementing our own language was because, again, it was the best way to leverage the capabilities of what our platform can do. We've looked at the syntax of Gremlin and Cypher, and it's doable that we could support them. They are, in a sense, a subset of what our language can do when we sort of map what can be done in our language. And when I say what can be done, I'm not talking about built-in functions, but I'm talking about more from a computer science standpoint. What sort of computability options does it offer? So we think our language is Turing complete. It's much more full-featured. So could we support Gremlin and Cypher? We believe we can, and we have long-term plans to do it. But so far, we think our best interest both for ourselves and for our customers is to really see how much you can do with GSQL. It definitely, we understand it would sort of smooth the transition for some customers who are already using Gremlin or Cypher. But so we do have long-term plans, but I can't give you a specific timeline right now.
Okay, thank you. The next one is around security, I guess. Does it support any kind of access restrictions with roles for users? Can I use my existing access management system like LDAP or AD? Does it integrate with them?
Mm-hmm. We have role-based access control. So, within our standalone system, you can define users. We have different roles. So, for example, we have a role for you can run queries. Another higher level of privilege is you can create and author queries. Another higher level of authority is you can create a database. So we have that sort of access control. We are also very close to deploying out. So I mangled that sentence, so let me start again. We are getting very ready to release our version that will support LDAP and Active Directory. So those sort of user management systems to sort of run across a set of applications, or we are supporting those, and will be released very soon.
Okay, and another question around like integrations. Does TigerGraph have integrations with Kafka and S3?
Yes, we do. We have customers in production who are using both Kafka and S3 together with TigerGraph.
Great. So I'm going to move over to the Q&A, and I don't know if you can actually look at those too, Victor. So the first one is, again, around the integrations. I think we just answered that one. Well, what other streaming data sources does TigerGraph support?
Okay. So the native format for our data input is either tabular, like CSV, comma separated values, though our loading language is programmable. It will support a variety of different separators and ways of distinguishing columns or tokens and providing some filtering. So it's sort of a lightweight ETL system. The other format, the two formats we support that we directly support are either CSV or JSON. We have some existing customers who are importing RDF data. So we worked with them to provide a preprocessor to convert that. And we've had a number of people ask about that. So we're probably going to be developing that as a sort of just a little tool to help people convert RDF and import it more naturally into our platform.
Okay, and then another question is, do we support, let's see, feature extraction and predictive analytics?
Right, so our platform its strength is that it is really good at a wide range of analytical tasks because of the flexibility of the language and the speed and data performance of the system. So we don't have built-in feature extractions. These are sort of machine learning tasks, but the system is capable of doing it because you can treat our GSQL language as a general purpose language which is integrated with graph traversal. So you can traverse the graph to gather your data, and then again with its computational abilities to implement your algorithm for feature extraction.
Okay, and then so there's two related questions. Is there an easy way to import a large RDF data set? I think you might have answered that already. For example, a dump of DBpedia or some such set. And related, how does TigerGraph support semantic web standards, RDFS and OWL?
Right. So again, we don't have a built-in customized interface for RDF import or semantic web. We have been talking with customers and potential customers who are interested in those use cases. They have seen that it is possible to do a preprocessor. We are, again, contemplating whether it makes sense for TigerGraph to offer this as a built-in product feature.
Okay. I think we need to clarify one of the earlier questions about S3, and the question was around S3 and whether TigerGraph natively supports IAM roles and the S3 protocol URLs.
I would have to go back to our design engineers to answer at that level of detail. I can just say that we have TigerGraph systems running on Amazon and also making use of S3 storage. And my understanding is they're just using combination of what is built into the Amazon services and what is available in the TigerGraph product to support the data transfer needs that they need. But I would have to go back to get a more detailed answer about IAM.
Yeah, we can definitely follow up with some of the questions via email. We have another question here. I think I skipped one. How restrictively, descriptively can you define the schema? For example, are there standard data types like relational databases for properties? For example, date, time, string, decimal.
Yes. The data typing is quite similar to what you find in relational databases. So some of those types named, date, time, string, integer, float, those are built into the language. If those actually, if I pop back here to the design schema and go to add vertex type and you look at the choices for attribute types, we actually have a couple more that are not shown here. Again, because it's hard to, we found it hard to express in the visual system. So if you're writing it out, you have, I'm referring to the complex types, lists and sets and maps. So I think, so again, designing a schema, it's pretty close to the way you design a schema for a relational database. So you'd be able to understand it very quickly if you're familiar with RDB. I think that was that question.
Okay.
I was reading ahead at the.
Okay. I think the last question here is what's the largest graph your customers have in production? Most queries per second, size on disk.
I think the largest is this one with Alipay. 100 billion vertices, 2 billion daily real-time updates. I believe they use 20 servers to support their system. And I believe that includes HA, so having replicas. So some of the servers are used to replicate the data. Let's see, queries per second. It's in the thousands, like around the 10,000 range. I don't know exactly. So I think on the order of 10,000 queries per second may be the fastest. It's really data dependent and query dependent. How complex is your query? But as far as largest graph and number of updates, I believe the Alipay one is the largest.
Great. There are a couple more questions in the chat. Do you provide full text search? And then after that, can you describe the pricing model?
We are not a document store, so we don't have as rich text features as you would find in a document store database. We do have string is a type. We do have some basic string manipulation functions. As for the pricing model, I would ask you to talk with our sales staff. I just speak in very broad terms that it's based on the amount of data that you have actually stored in our system. And again, since we compress our data, it may be less than you think because it's not based on the size of your raw data that's coming in. So it's not based per server, it's based on the amount of data that you're handling in, annual licenses.
Great. I think that is it. And we want to keep it under an hour here. Maybe you can go back to that final slide with the email. If anyone has any immediate questions, they can reach us at info@tigergraph.com. And then I think all of our social accounts are on there for more information. Once again, we recorded this presentation and we'll be emailing it to everyone who registered today. And then we have our website, we have our benchmark report and a bunch of white papers you can download on our website at a resources page. Do you have anything else to add, Victor?
I just want to thank everyone for attending today. Thanks for your interest. Thanks for your questions. And we hope we get a chance to talk with you further.
Great. Thank you so much, everyone. We appreciate it.